In this video, we're going to tackle a few questions, including what exactly is a dynamic routing protocol? Why do I need it? What are some examples of them and how do they work? All that and more coming up right now. So let's start off with the question of why use a dynamic routing protocol. Let's imagine that you and I are in charge of this network. Maybe it's headquarters network. And let's also imagine we have like 28 more networks. And here's how we're going to represent that. We'll have this router here. We'll put a cloud and we'll say we have 28 more networks in this cloud. Because that way we can just reference a group of networks or a group of devices without putting in all the details. So let's imagine we have these networks, 28, 29, 30, 31, 32. So we have a total of 32 networks. Now, in order for training, for example, a router like router 2 on how to reach all those networks, we don't want to do static routes. And that's one of the reasons we'd have a dynamic routing protocol that allows these routers to all talk amongst themselves. So when I think about dynamic routing protocols, I think about routers who need routers talking to other routers. And when I'm talking about routers here, I'm referring to layer 3 routing devices. So perhaps in this topology, we have some traditional routers. Maybe we have some multi-layer switches, which we'll talk more about later in detail. Maybe we have some firewalls who are also able to route at layer 3. And we could simply train all these devices here in this routing domain. That's another fancy way of saying all the routing that's under our control, if this is our company. And we could train them all to use a dynamic routing protocol, and then they could all share information with each other. So router 1 could share with, firewalls or other devices how to reach 10.1.0, and router 2 could share information about how to reach 192.168.50. So that way R3 would know about it, the firewall could know about it, router 1 could know about it. Effectively, all of our routing devices could learn the entire topology and how to forward traffic without having to do any static routes, simply by configuring a dynamic routing protocol. So in an organization, we're going to be running some type of a dynamic routing protocol. And in a company, we're going to call that an interior gateway protocol or interior gateway routing protocol. And I'll give you some examples of a few here in just a moment. But the one we choose is going to be based on what do all of our devices support. For example, if we have some devices that support one routing protocol and other devices that don't support that same routing protocol, we're going to have a problem. So we need some way of making sure that all of our devices are on the same sheet of music and they all can run the same dynamic routing protocol. Another factor to consider when we're thinking about a routing protocol is there's different methodologies that routing protocols can use as they share information with each other. One method that a routing protocol can use, I'll put methods here, is referred to as distance vector. And when I think of distance vector, I think of the rumor mill. Have you ever played that game where you start with one person, you whisper something to them, and then they whisper it to somebody else, and then by the time it's all at the very end, there's probably some distortion, it's not accurate? Well, that's what distance vector means to me, and here's why. Let's take a few networks specifically. Let's say 10.1 and 10.12 and 192.168.50 and the 10.23 network. And let's imagine that R2, who's the only one that's directly connected to 192.168.50, let's imagine that we're running a routing protocol and R2 advertises the 192.168.50 network over to R1, which effectively says, hey, Mr. R1, if you need to reach the 192.168.50, just send it my way and I'll take it from there. So R1 learns this. So now R1 in its routing table knows how to reach 192.168.50. But then R1, if we have another device over here, let's go ahead and take router 4. If router 1 then advertises that network of 192.168.50 via the dynamic routing protocol to R4, then R4 says, oh, great, to get to the 192.168.50 network, I'll send it to you, Mr. R1, and R1 would then send it to R2 and so forth. And also with distance vector routing protocols, as that route is being advertised, there's a certain metric or cost that's associated with that route. So R1 may see that network as like one hop away, one router away, and then as it gets advertised to R4, R4 may see that metric or the cost as 2 hops away. And that way, if router 4 learns about that same network some other way or through another path with the same routing protocol, it can say, wow, I've got one option that's 4 hops away and one option that's 2 hops away. I'm going to go ahead and choose this one with the better metric or better cost. And so with distance vector, oftentimes the metric is a hop or number of routers that packet has to cross to get to the final destination. So regarding R4 and these two choices, if it had another router over here that was also advertising that network, it could consider the distance, for example, the cost of how to get there, and also which direction to send it. Do I send it out to router 1 or do I send it over to this like router 6 device? And the rumor part of this is that R1 is not directly connected to the 192.168.50 network. R1 heard it from R2 And here R4 has now learned it through R1. So I consider it routing by rumor because R4 doesn't have direct and immediate knowledge from the horse's mouth regarding that network. We're simply passing along information about networks across our network topology if we're using a distance vector routing protocol. Now, probably the most popular and oldest dynamic routing protocol that is an example of a distance vector routing protocol is called REST in Peace. Well, that's the acronym. And the actual acronym stands for Routing Information Protocol, because we're basically sharing routing information across this domain, and that's the literal name of this routing protocol. It's called RIP. And I'm going to remove the periods because when we write out the word RIP, it's just RIP, which is the acronym for this dynamic routing protocol. Now, another method that a dynamic routing protocol could use to dynamically advertise networks inside of an organization or inside of a routing domain would be the method called link state. And let's have some fun breaking down what that means. If we have each router, let's just pick on router 2, for example. Router 2 knows, because it's directly connected, it's connected to the 192.168.50 network, and the state of that link is up. It's currently connected, it's up and active. It also knows that it's connected to the 10.12.0 network. That's another link that it has a network interface card, and that interface is up, and that's the network. And it's also connected off gig 0/3 to 10.23.0 network. So effectively, this router knows about those 3 networks and that it's directly connected. So what if we took that information? So we could say like R2 says that it has those 3 interfaces, those 3 networks. Then we take that as an advertisement, and then we propagate R2's advertisement to everybody. So we give R2's advertisement to R1, and let's go ahead and pick R4 over here also. And we also advertise that over here to R4. So the difference here is that R4 is not just taking R1's word for it. This advertisement about those 3 networks and the state of those networks is being propagated and advertised directly. So R4 has this little bit of information effectively directly from the horse's mouth, saying that, oh, R2 is directly connected to these 3 networks. And the same thing would happen for router 1. Router 1 would have 2 directly connected networks. We get advertisements from R1 regarding his information or her information. R4, we'd have information about R4 and its directly connected networks. And if every routing device that's running this link state routing protocol has that information, they can take all those pieces and they can build logically a map of where all the networks are. And then based on the best path or the best cost to get there, they can then choose and put into the routing table the best paths to reach any given network. And so it's not routing by rumor because we're actually getting those bits of information from each router that are being propagated across the network. And an example of a link state routing protocol that's very popular in an organization would be OSPF. And for the metrics involved, instead of using hop counts, like how many routers we have to go across, with OSPF, which is a link state routing protocol, it uses a metric called cost. So if R4 had a couple of different paths to get to the 10.23 network, one going through R5 and the other one going through R1, if one had a cost of 17 and the other one had a cost of 21, R4, as it's considering those 2 routes, can go ahead and choose the one with the better cost and use that as opposed to the route with the higher cost. So just as in distance vector, they're going to choose routes with a lower hop count, and with the link state routing protocol like OSPF, if they have multiple paths to the same network, it's going to choose the one with the lowest cost. And a long, long time ago, when RIP was first invented, RIP did not support the use of different length masks. So if you're using a /24, you had to use it everywhere. Or if you're using a /16, you'd have to use it everywhere with that same network. And as time marched forward, we started using variable length subnet masks, which basically means that we might need a /22 in one part of our network and a /20 in another part of our network and a /25 in another part of our network based on how many subnets we need and also how many hosts we need on those subnets, referring back to our subnetting videos. So with RIP, originally there was RIP, Routing Information Protocol version 1, which supported only a fixed length mask. And it had to be that same length of mask everywhere in your network. However, as RIP evolved a little bit, it didn't evolve that much, but as it evolved a little bit, we went over to something called RIP version 2, which does and has for many, many years support variable length subnet masks. So if we're running RIP version 2, it's advertising the actual network lengths. It's not assuming a fixed length mask. And because OSPF is a more modern protocol and it's more accurate due to being link state, it also supports variable length subnet masking, which means you can use a /16 somewhere in your network and or a /19 and or a /21 or whatever masks you want to use, because OSPF right out of the gate supports variable length subnet masks. So long story short, if you're using variable length masks in your network and you want to use a dynamic routing protocol, you'd want to make sure that you're using a dynamic routing protocol that supports the variable length subnet masks. And unfortunately, sometimes we inherit networks or we have to merge companies together, and perhaps one company is running one routing protocol and another company is running a different routing protocol and need to merge them together. So we might have, for example, this part of our network running RIP version 2, and over here, this portion of our network that's running OSPF. And if that has to be the case, where you just can't upgrade everything to the same routing protocol, we could use one device that is aware of both of those routing protocols and do a process called redistribution, where we take the routes from OSPF and we put them into RIP, and we take the routes that were natively learned in RIP and we move them into OSPF. And again, that's referred to as route redistribution. And from a network design perspective, it's a big no-no. This is more of a Band-Aid approach rather than the ideal design. But if you need to do the redistribution, you'd find a device that's running both the protocols and then do the redistribution of those routes between the two routing protocols on that single device. In this case, the example here is router 1. So RIP and OSPF are both examples of an interior gateway routing protocol, or IGP for short, and they're not the only two examples of dynamic routing protocols in this family of IGPs. Another routing protocol that's also link state, I'll go ahead and make an arrow over here, is called ISIS. And there's another protocol that was developed by Cisco Systems that's fairly proprietary, and some other vendors support it, but it's mostly proprietary, and that is a protocol called EIGRP. And with EIGRP, which has been around for a long time, and with EIGRP, it is effectively a distance vector routing protocol, but it also has some characteristics regarding link state because it actually forms neighborships and pays attention to who it's directly connected to. So oftentimes EIGRP is referred to as a hybrid. When it comes down to, is it link state or is it distance vector? It's kind of a mostly distance vector if you boil it all down, but a lot of people refer to it as a hybrid routing protocol. And again, those are all in the family of IGPs. Now, when networks get big, I mean really big, like hundreds of thousands of routes, and I'm talking about like the internet, we're not going to use an interior gateway routing protocol like RIP or OSPF or EIGRP or ISIS to coordinate all the effort between all the different service providers. So each one of these represents a service provider. We'll call it service provider 1, 2, 3, and 4 on the internet. And what they use as they dynamically share routes with each other is an EGP, an exterior gateway routing protocol. And in fact, to make this a very short discussion, there's only one, and that is BGP, the Border Gateway Protocol. And that is the dynamic routing protocol that makes the internet go around. So here's what you and I get to do. We're going to take a look individually at many of these protocols, including RIP and OSPF and EIGRP and BGP. And let me walk you through some of the nuances and details of how they work. So with that in mind, in the next video, let's take a closer look at this wonderful and very old protocol named RIP. Hey, thanks for watching, and subscribe right here to get the latest information from CBT Nuggets. And if you're new to or considering a career in the world of IT, head on over to CBT Nuggets and sign up for a free trial.